Thank you, Ollie. Cheers. Me and Anna are going to talk to you today about the problem we've been tackling over the last 3 days. And it's really simulating spatially variant rainfall and what this means to extreme flood events. Disclaimer, this is a very challenging problem. And we're not claiming to solve the curse of dimensionality overnight. However, we like to think that we've made some inroads into the problem, and we're going to disseminate them to you today. Can I just? Awesome. The overview of this talk, we're going to give you some background and motivation on the problem. We're going to really work with ONO's outreach project, Metropolis, and use this as a guide to our toy model that we'll be testing our methodology on. We'll then be covering the crucial component of this, which is a relationship between flood damage and your rainfall structure and intensity. And then we're going to formulate our problem and disseminate our results. This is a video of the Aire River in Leeds, am I right? Yeah, awesome. And this is water flowing very fast down the river and coagulating at the bridge here. This was Ono filming, and as you can see, this is heading towards the city, and this is very bad. All the water's being channeled into a tiny path, and yeah, this is motivation really. Cool. Spatially variant rainfall structures. As you can see, an area like this is not uniform rain, and this is currently what they're using, not this, a uniform tile of rainfall intensity. This isn't the case here, and obviously that will lead to very skewed results, and the output of your model would be off. This is something what we're after, but obviously there's problems about simply using this, and we'll show them in a bit. Assumptions, we have to simplify a problem a little bit to be able to move forward. First of all, we assume there exists some data, so obviously we're working with very little. However, we assume that you can apply this methodology to data, and the rainfall structures, at least on everyday weather, is when we get them, basically. We have to have some kind of measure of the cost of the damage of an extreme flood event. Now, we define our own damage metric here, but we'll show a plot that was shown to you by Group 4 to give you some confidence that our damage metric's along the right kind of lines of what we should be using. A little bit more about spatially dependent rainfall from that image I showed you 2 slides ago. This is just a 1D set of spatial coordinates. You can correlate your rain, and this is typically what's found. It can be binary, so either rain or no rain in a specific spatial coordinate, or it can be more gradual like this, and a continuous structure. Potential ideas that were thrown out of the bucket quite early. You've got kind of pattern recognition to our rainfall, so the idea would be we would create a rainfall structure library of different shapes. So this is on the far left, you've got a front of rain moving forward across the plain. Here in the middle, you've got a big ellipse of rainfall, and then here on the right-hand side, you've got sparse little blobs of rain. The idea would be to recognize which pattern you're onto and be able to sample from this. However, obviously, we chucked that out because it is high computationally expensive. We've moved on to the black box model, which basically has 3 stages. We sample our rainfall intensity and the structure of it. We run it through a model, and this will be our 1D toy model for now, Metropolis, but it can be generalized to pretty much any type of flood model. And we move on to try and get our outputs, so our surface water level. And you can calculate damage metrics from this. The middle one there is the real bottleneck computationally. This is what costs the most, and ideally we don't want our optimization to be going on over here, because we'll have to run that model lots of times. So we want to try and work on the space of the left-hand side over there. This is our toy model. This was shown yesterday over in the far corner there. This is the Watropolis model. It's an actual physical model, but we've also got two idealized cases on a computer that we can show you in a few minutes. Basically, it rains into, it's a stream that goes around in two S-shapes here. We've got two rainfall sources, one in the far end there and one in the middle here. And these can rain in different measures or quantities, so uniform rain. One rains heavily and one doesn't rain as much, or vice versa. And this changes the pattern as to your surface water level in the city over here, which is what we're really interested in. We can render this in 2D. This is from a finite element model of Watropolis model, and this will this is a work in progress, and this has been going on before the project this week. That's the city. This is just basically the S shape lined up in a 1D structure, kind of a straight line. You've got your city and the city walls just there in this far right hand side. What we're going to be working on is a 1D finite volume Watropolis model, and this is basically what you've got. You've got it straightened out again, but instead of the 2 dimensions, you've just got one. You run an across section of your river, so we can integrate the cross section here and use this as the scalar quantity that will be taken on a 1-dimensional grid. You've got your 2 rain sources and the city, which is what we're interested in terms of output. The impact metric and what we'll be measuring it causes hopefully the damage to our floods. We designed this and it's dependent on a few things. First of all, the rainfall intensity and the rainfall structure. So this is depends on our 1D function, and it's a function of time as well, which really does cover the Medway case in the problem formulation, where you had rain not just occurring in different places spatially, but also different times temporally. So we consider that rainfall intensity function R, and we assume that there's some damage metric. I talked about this earlier. This damage metric will we'll define it for now, but we'll also give an example of how this could be really attached to actual costs of flood damage in a bit, the next slide. Now that we've got both of those components, we can create the impact metric, which is this script I.
Is the symbol F in that integral meant to represent the damage metric D?
No. I'll go on to how this, what F is now. We'll introduce this impact metric, which is basically the integral over space and time of the rainfall intensity by some function F. And F controls the, you can optimize it or position it however you want to basically sample from the spatial structure of your rainfall. So F, it controls the distribution of your rainfall, and R is the intensity. F is currently uniform how they do it, so they'll just put rain in every place and at the same intensity and over the same time. Obviously, we want to try and optimize F away from a uniform one and towards an optimal one. That's our impact metric, basically. How do we simulate rainfall? Obviously, we need some kind of spatial correlation. This is an example of we basically simulate rain via a Markovian on-off type model. And this is the transition matrix between a rainy state R and a dry state D. It's just an example of one of the rainfall locations, so either X1 or X2. And this matrix just assumes they're independently transitioned, but we've also got a correlated one of these that correlates the 2 states together. We'll use both types in our results and methodology later. The hydraulic model, just to give you a bit of background behind Watropolis and how we simulate from it. So we compute via a finite volume method, as it's just in the 1 dimension, and it really runs on a kinematic model equations up there, where you've got your WRH, the product of those 2 is your cross section of your depth of water. And now we'll define our damage metric D. This is simply the take HC is the positive amount, if any, of water in the city, so the flood depth basically, times your velocity of water and integrated over space and time. So this doesn't take into account any cost to the housing in the city, and we'll show how that can be incorporated in a minute, but this does take into account flood depth. And throw back to a plot that was shown in the last challenge talk, we have the two of them, so flood level and cost benefit to the cities actually linearly correlating, or proportional anyway. So the two can be tied together, and hopefully we could tune that damage metric to create better results. I'll pass over to Anna now. She'll take you through the rest of the presentation.
That one's not okay. Can you hear me? No? Yeah? No? Now? No? Oh, you can hear me. Okay, cool.
Should I play it?
Wait, how does this work?
Oh, no.
Okay, cool. So we've simulated, yeah, perfect. So we've simulated rainfall and then the hydraulic model in MATLAB. So on the bottom here, you can see the rainfall at the two locations. So red is one location, black is the other location. And what we get out is the cross-sectional area of the river. And this is showing cross-sectional area along the stream of the river. And here what we're most interested in is the height of the river. Also, so the height profile down the stream. Where the red line is where we assume that there's a city. And so the height of the red line, we sort of assume we have some sort of barriers, and when those barriers are exceeded, we have a flood in the city. However, as we saw in the simulation before, we see that when the flood happens here, it's actually not at the same time as when it rained up the stream. So we have some this sort of time delay. So we have a problem of correlating the flood.
Run the movie again.
Sorry, Anna.
Run it again.
This is his work, so it's really happy.
So it will flood soon now, and then there's a bigger one coming. Yeah, there you go. Yeah, so we have a time delay between when the rain falls up the stream and when there's a flood down below. What we want is to sort of have a map between the flood and the stormy and rainfall that caused the flood. The way we've gone about this is just by looking at a typical time scales it takes for the rain that's dropped in the river to get to the city, to estimate that, and in order to quantify the time interval of rain intensity we want to look at to compute the impact metric. So we've got the damage, as Alistair mentioned, so we've computed that. We've got the rain intensity in order to calculate the impact metric. And the problem basically boils down to a minimization problem over the space of functions f. Ideally, obviously, we'd like to have an optimal f, but in reality, and looking at our model, we only have two locations. So we take just f at one location and f at the other location, and at each location we discretize it temporarily as well by just taking piecewise constant functions, so sums of Heaviside functions that determine the bin widths for f and r. Essentially, this then boils down to just a normal least squares problem, sort of like a regression type, for which we have an analytical solution, and it's therefore quite cheap to compute. So we've simulated the rain and run it through the hydraulical model for 500 days, And this time, so first we've done it for uncorrelated locations, so our model for rainfall simulation, the way rain falls at the two locations is uncorrelated, so we can have completely dry and like a wet day there. So by doing this, we've then trained F on this data, synthetic data. Afterwards, we've run the rain simulation again, and only for 500 days, and we've looked at results. So for uncorrelated, so if we have a uniform F, as Alistair mentioned previously, we have a uniform rain, so there's no bits where rain is more important for the flood, are just equally important. So we can see here that from the uniform F to optimize F, we have a slight, so the results are better because we have because the storms and the impact and damages are closer to the X and Y, X equals Y line. What we've done after is, because obviously we've looked at some other rainfall data that we found online. There's an rglim-clim package, which by doing a different rainfall simulation simulates rain that's correlated at the two spots. So we've trained our model using our correlated Markovian rainfall, and then used rglim-clim data to test it. And we find that the root mean square error from the uniform F to the optimized F is better. However, this one is quite sensitive to big outliers. So obviously, our model doesn't have, I mean, there's more testing to be done on real data sets, etc. So to summarize, we've devised a Markonian model for simulations of uncorrelated and correlated rainfall at two different locations. We've analyzed the output from the Metropolis hydraulic model with rainfall simulation as input. And so we've quantified flood damage and trained that model to predict flood damage from spatio-temporal rainfall intensity. However, so the way we simulate rain is by just looking at what's the total amount of rain that's fallen on a certain day, whereas we know that storms normally take a much smaller amount of time. I don't know, it can be a couple of hours. And so we don't have much insight into how the storm behaves over smaller amounts of time. As well as we only have two locations, so we don't have that much insight into the spatial impact of the rain. So in future, this model would have to be made more complex in order to show more significant results. We also, we need a way of identifying storms straight from the rainfall without putting it through the hydrological model. However, our toy model does provide a proof of concept, and exploiting spatial and temporal structure, we know that it requires quite a large set of simulations, but maybe that can be overcome simply by expert opinion. Yeah, thank you.
Thank you. Comments?
Am I okay? Yeah. Oh, thanks very much, guys. That was really interesting. I'm glad you got to work on the proof of concept with Metropolis. That's it's nice to see it actually in action. So if just to check I've understood your approach, you've drawn on something a bit like the continuous simulation type approach, but the idea is that rather than running the full model, you run it on your function, which is effectively an emulation of the model, so it runs very quickly, and then you can go back and rerun those events which are interesting on the full model to get the real insights. Yeah, I think that's quite exciting. I think to make this work in practice, we still need to do a bit of work. So we need to make it easy to get those rainfall patterns, and we need to figure out how we get that function created. I wonder whether we could train it based on data people already have about their model. So when you built a detailed model, you already know where the sewers are, where the properties are, And it might be that rather than having to train it so much, the stuff you already know about the model, you can create it. Or you can have a hot start effectively that gets you off quicker.
Yeah.
Yeah, this is the thing. We don't need the training data. Glim. Oh, do I need this for questions?
Yeah.
Okay. Thank you. Cheers. What we learned from the Glim experiment was I don't know if I can go back. Was that we were training and testing on different types of rain. So this applies to what you were just saying, which is we can train VF on something slightly different than the correlated data in which we were testing. And this plot, if anything, shows much more than the other uncorrelated one, because it really does tackle the spatial structure of your rainfall and testing it on a totally different set of data as well, which is cool.
But you do need the damage function to
You
train
do,
on.
yeah, for sure.
So if reality is your black box model, that's fine, right? It's perfect. But you do need the damage function.
Yeah.
And
So
correlate
this.
it to the distributed rainfall.
Yeah, it's really exciting. I think we've got some. The nice thing about the rainfall is we've got some ideas emerging. And so as Barry's talked about, we're developing simulation libraries as one of the trends in flood risk management at the moment, and I think that can be extended to rainfall as well, can it?
It's long term. I mean,
Keyboard there. Barry.
thanks. The work that Rob Lamb's done from the JBA Trust on spatial joint probability analysis and training, looking at the work of Hefferman and Torn on joint probability of extremes. We have been generating, say, 20,000 realistically spatially variable rainfall fields from long-term tipping bucket rainfall gauges. So there is that.
That would be really good to train Fs around and test Fs around both spatially correlated patterns.
So I think that's coming. And I think the other question, which is a good research question, a new research question, is about how do we develop that? How do we develop that function based on models we already have, and make that easy for practitioners to use?
Yeah.
But something to look in for the next Math for C's group, eh?
Thank you. Cheers.
Are there more questions? Yes, Tom.
So you put a key point at the end that was about the exploiting the structure, and it requires training of lots of simulations, and then might be overcome with expert opinion. Could you just elaborate on that a bit more?
Yes. So the F is the really important thing you need to train. So the complexity of F obviously is determined by the complexity of your spatial structure, whereas F has 6 piecewise points because it's only on two spatial coordinates and 3 points in time. Quite clearly ours is simple to train, whereas a more complex structure to F could revolve around going to an expert and going, I'm going to weight my F a little bit more keenly around there, or something similar to that.
So the expert is the practitioner or the person who's got
A good understanding of the catchment and the rainfall patterns in that area, yes.
Well, in principle, Tom, this is a really big problem because you would have to do this for all X.
Yeah.
So the experts, so you don't want to do it for all X. So we just did it for 2 here, but I suspect the expert can be used in saying which locations are deemed most appropriate to measure, so that you only have a handful of Fs rather than an infinite amount, which it is in reality. Are there further questions? No? Oh, yeah, very good.
Instead of the expert, you can probably also use altitude in some areas. Just
Sure.
Yeah, thank you.
Okay, join me in thanking this group. And then we'll close. You take one.